Throughout Jiren's ongoing research, I've made a simplified but comprehensive overview of his current findings. This is my interpretation of the first few months of his work on unifying quantum physics and relativity. While it may at times be difficult to follow due to the subject matter's complexity, it also has some philosophical implications which are addressed in the epilogue. Over the past century, many groundbreaking discoveries have led to scientific paradigm shifts in our understanding of the world. Einstein's theory of relativity revealed how time and space are the same fabric, while Niels Bohr's research helped us understand the building blocks of matter through quantum physics, a realm that only exists as an abstract physical description. Afterwards, Louis de Broglie discovered that all matter, and not just photons or electrons, has a quantized wave-particle duality. These breakthroughs have led to new schools of thought about the nature of reality and have inspired popular metaphysical and pseudoscientific theories, such as the human mind being able to command the universe through positive thinking. However attractive, these theories have no verifiable evidence and can slow down scientific progress. Einstein's laws of special and general relativity are applied in modern-day technologies, such as GPS satellites, where the accuracy of calculations would drift more than 7 miles a day, if consequences such as time dilation would not be taken into account. Time dilation is best illustrated by how moving clocks run slower. Other implications of relativity are length contraction, meaning that objects in motion decrease in length, and the relativity of simultaneity. It is impossible to say in an absolute sense whether two events occur at the same time when they are separated in space. Nothing can travel faster than the speed of light. This means that if a bar of 10 light seconds long would be pushed forward, it would take 10 seconds before the action can take place on the other side. Without this time interval of 10 seconds, the bar does not exist in its entirety. This is not due to our limitations as observers, but due to an inherent consequence of relativity, where time and space are interconnected and cannot exist without each other. Quantum physics provides a mathematical description of much of the wave-particle duality and interactions of energy and matter. It departs from classical physics primarily at the atomic and subatomic scales. The mathematical formulations are abstract, and the implications are often non-intuitive. A quantum is the minimum unit of any physical entity involved in an interaction. The elementary particles are the basic building blocks of the universe. They are the particles which all other particles are made of. While in classical physics we can always split things into smaller bits, for quanta this is impossible. As a result, the quantum world presents many unique phenomena that cannot be explained through classical laws, such as quantum entanglement, the photoelectric effect, Compton scattering, and many more. There are many exotic interpretations of our quantized world. The most widely accepted among physicists include the Copenhagen interpretation and the many worlds interpretation. Current trends show substantial competition from alternative interpretations such as the holographic universe. While both quantum physics and Einstein's laws of relativity are essential to our scientific understandings of the universe, there are many unsolved scientific problems, and thus far no unifying theory. Some of the current questions are: why is there more observable matter than antimatter in the universe? What is the nature of the arrow of time? What is the origin of mass? One of the most important keys to finding the answer to these problems are de Broglie equations, for which he was awarded the Nobel Prize in Physics. This formula shows how all matter has a wave-particle duality, meaning that there are moments in which it behaves as a wave, and others where it behaves as a particle. The formula combines Einstein's famous E is mc squared equation with the quantized nature of energy. Experimental evidence includes the interference pattern of C60 fullerene molecules in a double-slit experiment. The fact that our consciousness itself seems to be made up out of quantized particles has been the subject of many mystical theories. And while the relation between quantum mechanics and consciousness is unlikely to be as magical as recent esoteric movies and literature claim, there is nevertheless a profound implication. As de Broglie's equations apply to all matter, we can fundamentally establish that C equals hf, where C stands for consciousness, h for the constant of Planck, and f for frequency. C is responsible for what we experience as the now, a quantized or minimum unit of an interaction. The sum of all moments C up till the current moment is what shapes our concept of life. This is not a philosophical or theoretical statement, but an inherent consequence of all matter and energy being quantized. The formula shows how life and death are abstract constructions of C. Another consequence of de Broglie's equations is that the rate at which matter or energy fluctuates and acts like a wave or a particle is relative to the frequency of the frame of reference. Increases in frequency due to velocity are relative to others and bring about phenomena such as time dilation. The underlying reason is the unaffected experience of time relative to the reference frame, where space and time are properties of quanta, and not the other way around. Antiparticles are created everywhere in the universe where high-energy particle collisions take place. This process is artificially simulated in particle accelerators. When matter is created, antimatter is created simultaneously. Hence why the lack of antimatter in the universe is one of the biggest unsolved questions in physics to date. When we trap antiparticles through electromagnetic fields, we can study their properties. The quantum state of particles and antiparticles can be interchanged by applying the charge conjugation, parity, and time reversal operators. To clarify, if a physicist whose body was made of antimatter would do experiments in a laboratory also made of antimatter, using chemicals and substances of antiparticles, he would find almost exactly the same results as his matter counterpart. But when they would merge, immense energy would be released proportional to their mass. Very recently, Fermilab discovered how quanta such as mesons are switching 3 trillion times per second from matter to antimatter. When we study the universe from a quantized frame of reference C, we have to take into account all experimental evidence that applies to quanta. This includes how matter and antimatter are created simultaneously in particle accelerators, and how mesons switch back and forth between one and the other. This has significant consequences when applied to C. From a quantum perspective, every instance of C has an anti-C. This explains the missing symmetry or antimatter in the universe and is closely related to the arbitrary choice of emitter and absorber in the Wheeler-Feynman time-symmetric theory. The unperturbed time t in the uncertainty principle is the required time or cycle for quanta to exist. Similar as observed in mesons, our personal experience of time or interval of the current moment reaches its threshold when c is cancelled out by its anti-c. C's interpretation of this single self-annihilating moment is framed within an abstract arrow of time. If we then want to define interaction and look at the basic properties of the wave-particle duality of quanta, all interactions would consist of interference and resonance. But since this isn't enough to explain the fundamental forces, we are required to use different models. This includes the Standard Model, which mediates the dynamics of the known subatomic particles through force carriers, and Einstein's general relativity, which describes macroscopic phenomena such as the orbits of planets, which follow a curvature or ellipse in space and a helix in space-time. But Einstein's model of space-time doesn't hold up on quantum levels, and the Standard Model needs additional force carriers to explain the origin of mass. Without success, a unification of both models or theory of everything has been subject of much research. Quantum mechanics is merely mathematical descriptions, and their practical implications are often counterintuitive. Classical concepts such as length, time, mass, and energy can also be approached with similar descriptions. By building on de Broglie's equations, we can substitute these concepts with abstract vectors. This is a probability-oriented approach towards the basic and already existing concepts in physics that allows us to unify quantum mechanics with Einstein's relativity. De Broglie's equations show how all reference frames are quantized, including all matter and all energy. Particle accelerators have demonstrated that matter and antimatter are always created simultaneously. The paradox of how reality can emerge from abstract building blocks that annihilate each other can be explained by using these quanta as the frame of reference. In a simplified analogy, we need to look at things through the eyes of a photon. The reference frame is always a quantum and defines how space-time is quantized. When it increases or decreases, space-time increases or decreases as well. This is reflected in quantum mechanics as the mathematical description of the probability amplitude of the wave function, or in Einstein's relativity as time dilation and length contraction. For a quantized frame of reference, mass and energy can only be defined as abstract probabilities. Or if we want to be more concrete and establish a mathematical framework, as vectors which can only exist when we assume an arrow of time. They can be derived as resonance and interference with the reference frame, which defines the minimum unit or space-time constant c, equivalent to the constant of Planck in quantum mechanics. Experiments show how conversion of matter into energy through its antimatter brings about gamma rays with exact opposite momentum. What seems to be a conversion is the ratio between opposite vectors interpreted as distance and time, matter and antimatter, mass and energy, or interference and resonance within the abstract arrow of time of c. The sum of opposite vectors is always zero. This is the reason for the symmetry or conservation laws in physics, or why at the speed of c, time and space are zero due to length contraction and time dilation. A consequence is the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be known simultaneously to high precision. In a sense, a single particle is its own field. This does not explain our sense of continuity, where c cancels itself out within its own required interval. But when these vectors are exponentially amplified or accelerated relative to and within the abstract arrow of time, the underlying mathematical algorithms, also describing the fundamental forces, can bring about a consistent reality and have abstract building blocks. This is why the harmonic motion equations are used in many fields of physics involving periodic phenomena, such as quantum mechanics and electrodynamics, or why Einstein's equivalence principle, used to derive the model of spacetime, states that there is no difference between gravity and acceleration. Because gravity is only a force when interpreted relative to an oscillating frame of reference. This can be illustrated with a logarithmic spiral curve being reduced to a helix curve by the reference frame, making objects spin and move in orbits. Visually simplified, two amplified or growing apples will be interpreted to attract each other when observed by an amplified reference frame, as the size seems unaffected. The opposite occurs with interference. In a simplified analogy, the increase or decrease in the size of objects as we get closer or further away is determined by the shift in vectors of the reference frame, similar to how a radio homes in on different waves to pick up radio stations. This also applies to the influence of gravity. In essence, independently of any reference frame, there are no fundamental forces. All interactions within our abstract continuity can be mathematically derived through interference and resonance as long as the ever-changing and fluctuating minimum unit or quantum, being the frame of reference, is taken into account. Experimental evidence includes the unseen effect in the Standard Model, where we can see the force effect, but not the actual force carriers. The consistent continuity of reality does not require quanta to have any specific sequence in time. A quantum is not subject to any notion of space or time and can occupy all of its possible quantum states simultaneously. This is called quantum superposition and has been demonstrated in experiments such as the double-slit experiment or quantum teleportation, where every electron in the universe, for example, could be the exact same one. The only requirement for an abstract arrow of time and consistent continuity or reality is the algorithm describing the pattern or abstract sequence of vectors. Since this continuity brings about our ability to be self-aware, it inherently makes us subject to its mathematical consequences, the fundamental laws of physics. Interaction is merely an interpretation of what is essentially an abstract pattern. This is why quantum mechanics can only provide mathematical descriptions, since it can only describe patterns within infinite probabilities. When a probability is expressed as C, the information necessary to describe the current moment or probability amplitude of C is also what embodies the arrow of time. The nature of the arrow of time is one of the biggest unsolved problems in physics and has been responsible for many new popular interpretations. The holographic principle, for example, a property of quantum gravity and string theories, theorizes how the entire universe can be seen as an information structure of only 2 dimensions. Traditionally associate the notion of an arrow of time with the sequence of events that we experience through the arrangement of short-term and long-term memories. We can only have memories about the past and not about the future, and we've always assumed that this reflects the flow of time. Scientists only began to question this logic when discoveries in quantum mechanics demonstrated that some phenomena are not bound by our notion of time, and that our concept of it is nothing more than our perception of the change in observable values. This is also reflected in time dilation and length contraction, which are part of the reason why Einstein established that time and space are the same fabric. In an absolute sense, the notion of time does not differ from the notion of distance. Seconds are equal to light seconds, but cancel each other out. To clarify, with distance and time being each other's opposites, the passing of time can be interpreted as the distance that the hands of a clock travel as they move in a direction that is opposite to time. As they move forward in distance, they effectively travel backwards in what we would call time. This is also why any single separate minimum unit of experience is always instantly annihilated within a timeless now. This understanding sets the record straight between wave function collapse and quantum decoherence. Concepts such as life and death are mere intellectual constructs, and any speculative spiritual ideas of an afterlife that takes place in a realm where the rigid mathematical underpinnings of this reality come to an end are equally fabricated. An important cosmological consequence is that the Big Bang Theory, where the universe is traced back to one point by looking at the past, is a misconception. The traditional assumption of space-time, where space is three-dimensional and time plays the role of a fourth dimension, is inaccurate. If we would want to study the origin of the universe, we would actually have to look forward, since c's time vector direction is opposite to the arrow of distance, from which we perceive an expanding universe. Although this temporal mapping of the universe will only yield abstract concepts with no relation to its quantum underpinnings. Experimental evidence includes the accelerating expanding universe, following what is known to be an inverse or time-reversed black hole metric, as well as the many problems related to the Big Bang Theory, such as the horizon problem. These derivations could bring up questions about free will, since awareness seems to only take place after the action within our perception of time. Most neurological investigations that have shed light on this question show that action is indeed taken before becoming conscious of it. But a deterministic point of view is based on an erroneous concept of time, as is illustrated by the mathematical probability descriptions in quantum mechanics. These understandings will be relevant for future neurological research, since they show how any neural circuit is a vector with direction, underpinning cognitive dissonance and interference or resonance within C. The ability to understand and consciously alter these directions, acquired through billions of years of evolution, confirms how important our belief systems are in expanding our awareness, and how they affect our working memory, which is responsible for the extent to which we can make connections and for the neural processes that create meaning. It also explains how artificial awareness will require a network of independent processors instead of a linear sequence of complex algorithms. Athén's grand unification is one solution that unifies quantum physics and Einstein's theory of relativity. While it answers many problems in physics, such as the ones listed here, it is my limited interpretation of his first months of scientific research. Whatever the outcome, it is clear that we have entered an era where science is open to everyone. And if we can preserve unfiltered access to a neutral internet, we can test the validity of our ideas. We can enhance our imagination by making new correlations. And we can be part of the evolution of our understandings of the universe and of the mind. In quantum mechanics, we have learned to approach reality differently and see everything as probabilities instead of certainties. In a mathematical sense, anything is possible. As well as in science as in our daily lives, the extent to which we can calculate or figure out probabilities is determined by our intellectual capability to recognize patterns. The less biased we are, the clearer we can identify these patterns and base our actions on reasonable probabilities. Since it's in the very nature of our brain's left hemisphere to deny ideas that do not fit into our current paradigm, the more attached we are to a belief system, the less able we are to make conscious choices for ourselves. But by observing this process, we expand our awareness and enhance our free will. It is said that wisdom comes with age, but with openness and skepticism, the key principles of the scientific method. We don't need decades of trial and error to sort out which of our convictions may be improbable. The question is not whether our beliefs are right or wrong, but whether or not being emotionally attached to them is more or less likely going to benefit us. There is no such thing as a free choice while being emotionally attached to a belief system. The moment we are self-aware enough to realize this, we can truly work together to figure out the real odds of what will benefit us the most.